and it works. Okay. So let me remind you what we have done in the case of discrete random variables. Okay. So in the case of discrete random variable, I was in this situation, and in the discrete case, it means that the range may be written as a countable family of possible points. Okay. This one. In the discrete case, I have this situation. So I have defined in this situation the space LP that are the space where I am able to define the expectations. Expectation of x, expectation of x squared, expectation of x to the power p. So it's the set of x that is a discrete random variable. And I impose an extra condition to be in LP that is just the sum of the absolute value of xi to the power p probability that x is equal to xi. I want this sum to be finite. Okay? In particular, if I take p equal to 1, or p equal to 1, I have a 1 here. Okay, so I have the absolute value. And typically, we have seen several things. We have seen the same proposition as this one, that is, if p is less than q, okay, you have LQ that is included in LP. Okay, we have decreasing spaces. I have done the proof in this situation of this one. If you remind, cutting the sum in two parts. Okay, I use the property of the power function, but that depends on my position with respect to 1. If I am between 0 and 1, I have one property. If I am greater than 1, I have another one. So you have to cut, okay, and use these two parts separately. And I have done the job in order to say that if you have something that is in L1, I am able to define the expectation of x. That will be now a finite number. It won't be plus infinity, or it won't be something that is not convergent, but that may be expressed as this one. Okay, and I know that if I am in this space, this sum is okay. And the last thing I have done is that if I am in L2, I can define the variance of x as by the same thing, not the same thing, but I can define it through the expectation. I can define it, for example, this way. And everything is well defined here, because if I am in L2, it means that the expectation of the square is finite, so this term is okay. And if I am in L2, I am in L1, so the expectation is also well defined. Okay, so both terms in the definition of the variance are well defined if I suppose x in L2. But here I will do exactly the same. Okay, so now suppose that you are in the situation where, okay, you have x random variable with the density f of x. Okay? As I have defined in the discrete case LP space this way, we are going to do exactly the same. So LP is the set of the random variables x with density such that here I add the sum of the absolute value of the power p multiplied by the probability mass function that I will replace by the integral x to the power x. That is exactly this one. So you see the link between both. In the discrete case, I have a sum of the possible values to the power p with absolute value, okay, multiplied by the probability mass function. in the continuous case, integral of my possible values multiplied by the density function. Okay? So if I do the job this way, but it should be possible for me to do finite, of course. Huh? I have an integral here that has to be finite. So it's a proof that I want to do, but that you have in the list of proof, exactly in the same way that I have done the job for the discrete case, that is separating in the parts, okay, greater than 1, less than 1. I can do the job with the integral, okay, and say that if P is greater than Q, LQ is included in LP. In particular, L2 is included in L1 here. If I have X that belongs to L1, I can define the expectation of X this way. And finally, if I am in L2, the variance of X may be defined as the expectation of X squared minus the expectation of X. So in fact, you have nothing new to learn. Just the fact that dealing with random variables having density will make you use integrals instead of sums. Okay? So if I have a look on the next slides here, but you have the definition of the space I have written on the board. You have this proposition with the proof that will be in my list of proofs. Then what I have the definition of the expectation here. Definition of the expectation, okay, that is exactly what I have written here. We are going to do now the computation in classical cases, okay. In the last slide, I have the definition of the variance, the definition of the standard deviation, the definition of the covariance, and in fact, this slide is exactly the same, nothing changed, nothing, that the one I have done in the case of discrete random variables, okay. You have the same property, so the covariance is something that is bilinear. If I have independence, covariance is 0. And I have these rules of computations for the variance of the linear combination. So the only thing that we are going to do here is just to do also the computation for classical cases, okay, and see what happens. So before to do this computation, just a little remark. So you have here a big proposition, okay, concerning the properties of the expectation. Once again, the proof of all of these statements are in the list of proof.
Sir?
Yeah.
The P super is smaller or equal to Q, and then the LQ is including LP. So the continuous variable cases.
Yeah. What have you done? Oh, yeah, right. Early in the morning for everybody. Okay, so look at here, I have written this one that is correct. LP spaces are decreasing, so I have L0, L1, L2, and so on. So here, I have written something that is okay, and here, a little mistake here. Okay? So I want to change, make it okay. This one, thank you. Okay. I have the same property for sure. Okay. L0 contain L1, that contain L2, that contain L3, and so on. Okay? So just a remark concerning this proposition, because typically for these three here, I have just copy and paste what I have written in the case of discrete random variables. So it's nice for me, I don't have to work, okay, it's perfect. When I want to write this proposition, okay? So what is the meaning of this one? Some properties we have seen in the discrete case, that the expectation is linear. The expectation of a linear combination is a linear combination of the expectations. The fact that if you have two random variables that are in L2, the product is in L1. The fact that if you have two random variables such that the product is also in L1, that is, you can consider the expectation of X, the expectation and the expectation of XY. If they are independent, the expectation of the product is equal to the product of the expectations. Exactly the same relation as in the discrete case. And I have here what I have called the Jensen inequality related to convex mappings. Okay, that tell me in particular, if you consider in this expression as a convex function the square, you have the square of the expectation that is less than the expectation of the square. That is another way to see that my variance is in fact something that is positive every time. Okay. The only thing that is changing with respect to what I have said in the discrete case are this one in fact. Okay. And keep in mind what I have said to you in the discrete case. In the discrete case, we have seen together that, so I am in this situation here. We have seen together that if I want to compute the expectation of j of x, okay? So a priori, if I come back to the definition, in order to have the expectation of j of x, I need to know the probability mass function of j of x, and to know it perfectly. But I have a formula that tells me that if I know the probability mass function of x, it's sufficient in order to compute this kind of expectation. It's not necessary for me to know perfectly what is the distribution or the probability mass function of j of x, but it's only sufficient to have the probability mass function of x through this formula here. That is the sum I belonging to capital I. And what I do, I take the possible values for j of x that are j of xi, probability that x is equal to xi. Okay? This formula we have seen in the discrete case. Here I have exactly the same thing. In this situation here, if I know that x has a density function f of x, if I want to compute this kind of expectation, that is the expectation of a function of x, okay, and if I want to be able to write, so I want this one to be in L1, that is the expectation is well defined, okay. How to compute? Here I have the sum of j multiplied by the probability mass function. It's just the integral of j multiplied by the density function. So the analogous of this formula, okay, for a random variable having a density function. So if I know the one in the discrete case, if I replace sum by integral and probability mass function by density, I obtain exactly the same thing. Okay? And this one, that is just a generalization of this one. So during the previous session, we have spoken about random variables that are jointly continuous. That is the one with a pair that are pair having a density function. We have seen consequences of this. And I said that if x and y are jointly continuous, if it has a sense to compute this expectation, in order to compute this kind of expectation, that is the expectation of a function of x and y being jointly continuous, what I have to do, but instead of having to know the density function of this random variable, I can just compute it if I know the joint density. So it's the double integral of the mapping j at the point small x, small y, multiplied by the joint density function of the pair. So it is the analogous of this formula, here in the case of a single random variable that is continuous and with a density function, and here in the case where you have two that are jointly continuous. Okay? So it means that in order to compute for one or even also for jointly continuous random variable, in order to compute expectations of function of this random variable, you will just have to compute integrals with respect to density functions. Okay? So now we are going to compute a little, okay? And mainly, so it remains to have a look on the slide 14, I will do just after, but the part concerning continuous random variable is finished now, okay? And now, the only job you will have to do, okay, is to be able to compute integrals. We are going to see that all the things and the exercise that we are going to do now will be related to the computation of integrals, and it will be for at least 1 month that we will compute integral. When I will go back to the statistical part, okay, we will do other things, but below now, okay, if you are able to compute integrals, knowing few definitions will be okay for you. Okay. So I have to work a little. I have to do computation in classical cases. Okay? So it's what we are going to do. Do you have questions? Okay? So I erase everything. Now you have the parallel between continuous and discrete. Okay? Exactly what you need to have in mind. So let's compute expectations and variance in the classical case. Okay? So if I am a uniform on the interval AB. So first of all, I need to know the definition if I want to compute something. Okay, so what is the density function of this one? What is the density function? Every day, almost every day, not every day. At the moment, the probability of being late is 1/2, more or less. Yeah. So it's the indicator function of AB over B minus A. Okay? This is the density function of a uniform we have seen here. So here I have said you that I have written strictly here, but you can put strict, large, whatever. We are in the continuous case. Okay? It changed nothing in my computations. Okay? But in general, we include the thing inside the product. Okay, so I am interested in the computation of the expectation. Okay? So I want to deal with this one. So a priori I have to be careful because I have an integral to compute on minus infinity plus infinity, and sometimes it is possible that this integral doesn't exist or is plus infinity. Okay? But here it's not the case because I have an indicator function in the density function, so it means in fact it's not an integral from minus infinity to plus infinity, it's just an integral between A and B. Okay? So it is the integral of a continuous mapping on a compact interval, no problem of definition. It's the Riemann integral you classically compute, okay, without any particular problem. So it's this one that I have to compute. Okay, I just plug inside the density function. I have the indicator function that puts the new bounds in the integral. Okay, and I have to compute, so the integral between A and B of x over B minus A. But I have a primitive of x, okay, so it won't be complicated to compute. What is the primitive of x? X squared over 2. So I can write the thing this way. I can write it directly this one. X squared over 2 B minus A that I have to take between B and A. So to compute an integral, I would just have to take the difference of the primitive between B and A. It's the notation you have in the document in my site. And so I have what? I have B squared minus A squared over 2 B minus A. Okay? Something that I can simplify a little. What is this? B squared minus A squared is A plus B factor of A minus B. And at the end, I have B plus A over 2. What's that natural? Here I have a uniform on the interval AB. If you consider the expectation as the best approximation of my random variable by a constant, well, the one you obtain is just the middle of the interval. Okay? Not that surprising here. In particular, the expectation of a uniform on the interval 0, 1 is 1/2. Okay? the expectation of a uniform on the interval minus 1, 1 is 0. So you have this. Do you agree? It's a little computation, so nothing to do with proba, in fact, just computations of intervals. If I am interested in the variance, I will do both at the same time here. If I am interested with the variance, well, if I come back to the definition of the variance, it's the expectation of x squared minus the expectation of x squared. I know already this term, that is the square of what I have written before. Okay, and I have to compute this. So the expectation of x squared in this situation is what? So here, keep in mind what I have said here. If I want to compute the expectation of a function of x, I compute the integral of this function multiplied by the density function. So here, it's simply and I obtain what? So I plug inside my density function. It's the integral between a and b of x squared over b minus a. I have once again a polynomial to integrate here. What is the primitive of x squared? It's 3 over 3, and the primitive of xn is xn plus 1 over n plus 1. Okay? So it's x cubed over 3 b minus a that I have to take between b and a. I obtain at the end, okay, b cubed minus a cubed over 3b minus b. This is the expectation of the square. Okay. So if you are not okay with integrals, okay, I think that it's a good idea to spend time during the holidays to compute integrals. Okay? Or for sure you will have problem. For sure. Okay? You won't have problem necessarily with what we have seen together in the course, the definition and things, but when you will have to compute, if you are not able to compute, okay? So I want to compute the variance. I have the expectation of the square that is given by this expression. I have the expectation of x that is given by this expression, but I have just to plug inside and see that the variance of x is equal to b3 minus a3 over 3b minus a minus the square of this one, b plus a over 2 square. And of course, we are going to simplify a little. So, here you tell me that b square minus a square is equal to a plus b factor of b minus a. I have the same for b3 minus a3 here. You have b3 minus a3 is equal to what? It's equal to b minus a factor of it was b square plus ab plus a square. Okay, it's b3 minus a3. Yeah. Let me finish to write. Over 3b minus a. Okay. And here I have b plus a square over 4. So of course I can simplify here. And if I want to put them at the same denominator, okay, I will obtain something over 12. What is over 12? So I have to multiply this one by 4 and divide by 4, multiply this one by 3 and divide by 3. So I obtain 4b square plus 4ab plus 4b square minus 3 times the square here. That is minus 3b square minus 3a square minus 2a, excuse me, minus 6 AB. Okay? And I see that I can simplify a lot. Okay, I can simplify a lot, and I will write the results here. What I obtain. So I have 4 minus 3, 4 minus 3, 4 minus 6. So I obtain a squared plus b squared minus 2ab over 12. And I see and I remark that I have in the numerator a minus b squared over 12. Okay? So this is the variance of a uniform on the interval AB. A minus b squared over 12. Okay? So it's the square of the length of the interval divided by 12. Okay? So typically for uniform on the interval 0, 1, you obtain 1 over 12 as the variance of a uniform on the interval 0, 1. Okay? For uniform on the interval minus 1, 1, for example, you obtain 1 over 3 as the variance. Okay? And so here, nothing complicated because first I have in fact integrals on the finite interval and I have integrals of functions where I know primitives. Okay, so it can't be simpler in fact. That's why I have started with this one. So if I continue with the classical random variables, I have the uniform here. Let's pass to the exponential. Okay. So the density is given by lambda exponential minus lambda x. But be careful, I have a condition on x. Okay? X has to be here this way. Okay? If you forget the indicator function, you don't obtain a density anymore. Okay, so the indicator function is mandatory here. Okay, so we are going to try to compute the expectation in this situation. We are going to try to compute the expectation. We are going to do. So here typically I will have so this is the definition and I have to deal with an integral, but contrary to the previous case, okay, I will have infinite bounds in my integral. Okay, so it will be the integral between 0 and plus infinity because I have my indicator function here of x lambda exponential minus lambda x dx. Okay? I have this one to compute. Okay? So typically here, you can try to find the primitive for x times exponential minus lambda x. So you can try, but it will take you a long time because it doesn't exist. Okay? You don't have a primitive for sturdy mapping. So when I say don't have a primitive, I don't have a primitive that I can express using classical formulas. So it's not the formula you have to know here because you don't know. So what can I do? So I am typically in the situation where I know this. What is the integral without the x? 1. It's the integral of a density, 1. And I am able to do this because I know a primitive of this one. So in some sense, if I want to compute this one, I have to make disappear the x here. Okay? If you remind when I had computed the expectation using sums, okay, when I want to do this kind of thing, it was possible to, for example, to change the variable or something like this, okay? What can I do here? So it's a classical tool, okay, when you want to compute expectations, or when you want to compute integrals, you want to come back to something you know. Okay, what can I do? Nobody? So they are
Change variable. X lambda is equal to
x equal to
some
2?
t.
If you take x equal to t, it will be very nice, but you will change only the name of the variable.
No, x lambda. X lambda. X multiplied. Something like this.
Well, it will change nothing here.
No.
The only thing that it will change is that you will have dt.
Yeah, and after this.
You will have to integrate t exponential minus lambda minus t. That is exactly the same difficulty as the previous one.
Because after this I used integration by part.
The idea is integration by part. Okay.
Yeah.
The change of variable is not that necessary in this situation. Okay. But integration by part, yes. So first, keep in mind that I have an integral over an infinite set here. Okay. And I remind you that a priori, if you want to compute this integral, you have to compute a limit. Okay? It's this that I have to compute. The limit when a goes to plus infinity of the integral between 0 and a. This is the definition of the integral between 0 and plus infinity. Okay? So it's not necessary to do in general this intermediate step, but here I just, since it will be the first time we do an integration by part together, okay, I prefer to do it with finite bounds, okay, instead of taking into account at the same time the fact that I have an infinite bound inside. So what is the integration by part formula? The integration by part formula is not something that is complicated, okay? It comes from the following. If I ask you to compute the derivative of this one, what is it? Classical formula for the derivative of a product. Okay? Let's integrate this equality between a and b. Two numbers, arbitrarily. Okay? I have integral between a and b of f of x, j of x prime dx. That is equal to what? Integral between a and b f prime of x, j of x dx, plus the integral between a and b. This one, f of x, g prime of x dx. Here I have the integral of the derivative. So I know that the primitive of a derivative is a mapping itself. So here you have f b g b minus f a g a. And you have the integration by part formula. Okay? Integration by part formula is not something that is new for you. It's just when I integrate the formula for the derivative of a product, I obtain what is called the integration by part formula. Okay? So when you want to compute the sum of this kind of integral here, it is the difference of the product of the mappings. So the idea is to use this formula. So in general, it's not the way we write, okay? We write it as this one is equal to this one minus this one. Okay, but it's exactly the same. So we are going to use this one in this situation here. Keep in mind that I want to make the x disappear. And a nice way to make x disappear is to compute the derivative of x, because I will obtain 1. Okay? So if I define this one as, let's write it, j prime of x Right? So it's because it's the first time that I do this. After I will do integration by part. Okay, so here I remind you the methodology one time. Okay, then you have my list of reminders concerning integrals. Okay, and if you are not okay with this one, take time during the holidays to be. I have this. And why I do, stupid what I have done here. But if I do this, I won't obtain what I want. Because I want to compute the derivative of x. So it's more, I can write it this way. It's this one that I want to compute the derivative. And this one that I will be able to integrate or to find the primitive because it's a negative exponential. So if I apply my formula, I obtain the limit when a goes to plus infinity of what? Well, so I have this one is this one. So I obtain this one minus this one minus this one. Okay? So it is. So what is f? In this situation it's x, so f prime will be 1. J prime is this one, so what will be j here? What will be j? Minus exponential minus lambda x. Okay? Because the primitive of exponential minus lambda x is exponential minus lambda x over minus lambda, and I multiply by lambda. Okay? So if I do the job, I obtain what? I obtain a exponential minus lambda a is a minus before plus 0 and minus the integral between 0 and a of what? Of f prime, that is 1, and this one that is exponential minus lambda x. The integration by part formula apply to my problem here. If you want, in my situation here, I have f of x that is x, so f prime of x that is 1. I have j prime of x that is lambda exponential minus lambda x. So j of x is equal to minus exponential minus lambda x. You apply the formula, and you obtain this. The 0 comes from the fact that when I do f times j, if I take x equal to 0, I obtain 0 from the fact that f0 is equal to 0. Okay. So I have to compute this limit. Okay? What is this one? What is the limit of this one here? You have a polynomial against a negative exponential 0. So this one goes to 0 when n goes to plus infinity. And if I want to compute the limit of this one, okay, I just have to question. I don't with the math and so. Hmm? No. The inverse of what? Here? Where? Show me.
What is a minus sign?
Because it's the definition of the primitive. When you will compute the derivative of this one, you will obtain exactly this one. Because it's because you have a minus here. Okay, so if you compute the derivative of this one, you obtain exactly this one. That is the definition of being a primitive of. Okay, you have to know the formula. Okay, perfectly. You won't have the time during the midterm of the final exam to recover primitives. Okay, so you have to know them. And typically, what you have to know by exponential, okay, you have to know the polynomials. It will be more or less what we will use in this course. Okay? So you don't need too much, okay, but the more classical you need to know. And if you have a doubt, okay, here, to be sure that this one is the primitive of this one, but compute the derivative. In general, you know the formula for the derivative, and recover what you have initially. It will be the way to check that you are okay in the primitive. If you don't find the initial mapping, okay, it doesn't work what you have done. Okay, so I plug and I obtain this, so it remains to compute this integral here. and to take the limit. So if I summarize, may I erase this? So everything is explained, okay? Everything is explained. Now you are here. Here. Okay, you have here change of variable, gamma, you have where is the integration by part? I don't have integration by part in my document. Yeah, I have integration by part. It's here. Here, okay? And it is explained, okay, as I have explained to you with some examples. And the example you have here is exactly what I do now. So that's why if you have read this one during the holidays, it's not that surprising to do this because you have it inside here. Okay? So, have a look at home. Okay, so erase. And at the end, I am interested in the limit. When a goes to plus infinity of what? Well, the remaining terms, that is this one. I have minus minus, or I have plus. Integral between 0 and a of exponential minus lambda x. I am able to compute this one because I know the primitive of the exponential. So you see that I start from this integral with the x, and at the end the x disappears. It's exactly why I use an integration by part. Okay. And what I obtain here, the primitive of this one is exponential minus lambda x over minus lambda that I have to take between 0 and a. So it is equal to what? It is equal to 1 over lambda minus exponential minus lambda a over lambda and what happened for this limit? This one goes to 0 because I have a negative exponential. And I obtain 1 over lambda. The expectation of an exponential of parameter lambda is equal to 1 over the parameter. Okay, it's equal to 1 over the parameter. And here, in order to obtain the expectation, we do an integration by part. Okay? So just have a look here, and it's something that I explained in my notes here. So I come back to the definition of the integral from 0 to plus infinity as a limit, but I can do directly this formula this way, in fact. With directly, okay, 0 and plus infinity inside, not passing with the limit. So if you are not fluent with this, write this one, okay, in order to avoid mistakes. But if you already know to do integration by parts, you can do directly the things, okay, without computing limits and just handling integrals between 0 and plus infinity directly. Okay? So for this one, it's up to you, depending on the way you are able to do the computations. Okay? But typically, I won't do this every time, okay, if I need an integration by part. I will do it directly, having the formula in mind. Okay, so I have the expectation. Are you okay with this? It's not the first time. I hope that you heard about integration by part. Okay. So I use it here in order to compute my expectation. So expectation of x, 1 over lambda. Okay? May I erase my board here? So I want the variance now. If I want the variance, I come back to the definition of the variance. And the variance of x will be the expectation of x squared minus the expectation of x squared. I have already done the job for this term, and it remains to compute this one as usual. I go quickly and I obtain what? Integral between 0 and plus infinity of x squared, okay, lambda exponential minus lambda x. Okay? So I have this one, I have to compute. What can I do? But the idea is that what I have done previously, I have done the job for the same with x. I want the same for e squared. But once again, we are going to use an integration by part in order to compute the derivative of x squared to obtain 2 times x and to come back to the previous case, in fact. Okay? So if I do an integration by parts that I will denote from now on, I, B, P. Integration by parts. Okay? So I do the job here, and what I obtain. So here I will have my F. I have here my J prime, okay? And now I can use the formula. So it is x squared and exponential minus lambda x with a minus before between 0 and plus infinity. And I have minus the integral between 0 and plus infinity of 2x minus exponential minus lambda x dx. So it's the integration by part formula here. What is this term here? The limit of this one at plus infinity is 0, because I have a negative exponential here and a polynomial before, but the exponential is the best as limit at plus infinity. At 0, also 0. So I have in fact only this integral to compute here. That is plus 2 integral between 0 and plus infinity of what? Of exponential minus lambda x dx. No. This one. Okay. Now, how to do the job now? But in fact, it's almost what I have computed previously, this one. If you come back to the expectation is what? The expectation is the integral of x times this quantity here. I have just the lambda that is missing. So I won't, in order to compute this one, I won't use an integration by part anymore because I know my result, my previous result. So if you multiply by lambda here and divide by lambda, okay, you know that here you make appear, and you will see that it will be something that I will do a lot in this course to make appear what I know. Okay, that is in order to compute integrals, also to keep in mind that I have some integrals that are well known from the course. And this one is what? Well, it's exactly what I have computed here. It's the expectation of an exponential of parameter lambda. So I obtain 2 over lambda squared. Okay? 2 over lambda squared. Yeah. And finally, if I compute my variance, expectation of x squared is equal to 2 over lambda squared minus 1 over lambda squared, that is 1 over lambda squared. Okay? So you have this one, and can do the job. Okay? So you have to know these two results, okay, and also to know by how I can obtain them very quickly. And the idea is to use integration by parts. Okay? Okay? Okay. So it remains this one. Gaussian. So are you okay with the computation I have done on the board? So I will erase in order to do the job for the exponential, for the Gaussian. So let's start here. So my job, okay, is to do the computation of the expectation of the variance of this one. Okay. But the fact is that I want to be able to do, okay, less computation as possible. I don't want to compute. Okay. So it should be possible to do this directly, okay, to see what happened, but we are going to see what happened first, not for n m sigma square, but first I will suppose that x follows the n01. And why I do this? Because I have this proposition here. I know that if I have a n m sigma square, or this way, or this one, excuse me, so if I start from n01, if I consider m plus sigma x, it will follow this. Okay? So if I know the expectation and the variance of this one, from proposition 13 statement A, I will be able to obtain the expectation and the variance for all the exponentials. The advantage of this one is that a lot of coefficients disappear because I take m equal to 0 and sigma equal to 1, so I have a nice expression, or an expression that is a little bit simpler than with general parameter. So in this situation, the square root of 2 pi exponential minus x squared over 2. And often, through this proposition, it is always possible, always, not always, but often possible, to deduce from properties of n01 properties of nm sigma square. We will see that it will be true for the expectation and the variance. Next week it will be true for the moment generating function. It will be true for the conditional density, and so on and so on and so on. Okay? So if I do the job for this one, in general I do the job for all of them. Okay. So I have my density function here. I want to compute the expectation. And I said that in this case, the computation take half of a line. So, suppose that you have this one to compute, okay, and you want to use computations, okay, more or less as usual. What can you do? Here, if I try to do an integration by part, it will be a little bit complicated because, I can do, but because suppose that I use the same idea as previously. I said that I will compute the derivative of this one in order to make the x disappear. But if I take the primitive of this one, I have a problem because I don't have a primitive for this. So this idea is not good in this situation. Okay. Other idea is to say at the beginning, okay, is it possible to find such a primitive, find the primitive of such a mapping? In fact, yes, in this situation, you have a primitive for this one. Because you have something of the form, so it's not what we are going to use to compute, but to remind you that if you compute the derivative of an exponential, of a function, of a mapping, you have u prime x exponential u of x. But here you have exactly something of this form here. Because you have exponential of this mapping, that is u of x. If you compute the derivative of this one, you obtain minus x. Okay, so using this formula, it's possible to find up to a constant the primitive of this mapping as a negative exponential with x squared over 2 inside. Okay? So I say that it's possible to compute directly because I have a primitive for this one from this formula that tell me that the primitive of this one is just exponential of u x. Okay? But it's not the way I will do. You can try to do at home in order to train, okay, but it's not the way I do. Why I say that in fact it's not necessary for me to compute. structure here. Okay, so my objective is not to plot correctly this mapping, okay, but just to have a look on what is it. So at 0 it's 0, okay? And the limit in plus infinity and minus infinity is 0. Okay, so I have something like this. It's not perfect what I will say, but I will have something like this. And what happened for the for the negative part? Okay, I obtain something like this. In fact, I have a symmetry because here you have, okay, so if I give it a name, that is H, I have H of minus X that is equal to minus H of X. So I have a mapping that is odd. What happens when you do the integral of an odd mapping on a symmetric interval? 0. Because you see that if you have the curve here, keep in mind that the notion of integration has an intuitive interpretation in terms of area. Okay? So here you have the integral between 0 and plus infinity. You have here minus the integral between, or the integral between minus infinity and 0, and you see that if you do the sum of these two, I have a positive part, a negative part, at the end I obtain 0. So once you have a mapping that is odd, its integral is always 0. Okay? Odd in the sense that h of minus x is equal to minus h of x. Okay? So typically, so that's why, I don't know, the integral of x to the power 3, okay? It's not a good idea, but we use this one because the integral is not finite in this situation. But if you take a typically exponential minus x squared, okay, with multiplied by x this way, but you have something that is this way, I have an odd mapping with an integral that would be equal to 0. So I don't need to use the primitive here, but just to say that I have an odd mapping, so its integral is 0 without any type of computations. Okay, I don't need to compute. Of course, my argument is not true if I have a nm sigma square instead of a n0 1. Because if you take a Gaussian random variable, okay, the density is an even mapping, and so x times the density is odd if you have a mean equal to 0. So you have to have this symmetry with respect to this one here for the density function. So that's why I do the job for this one, and typically with the mean 0, because I can use symmetry of the curve. Okay. So my expectation is by 0. Okay, for this one. It's nice because I don't have to compute. It's clear, this argument, for everybody? Just to be clear, if you know a few things about integration. If you integrate even mapping, the integral between minus infinity and plus infinity is 2 times what happened between 0 and plus infinity. If you integrate odd one, the integral is 0. When it exists. So I do the job now for the variance. Okay, for the variance of this one. So if I want the variance, I need, since the expectation is 0, the variance will just be the expectation of the square. So I am interested in the expectation of x squared minus infinity plus infinity x squared multiplied by the density of my n01, that is 1 over the square root of 2 pi exponential minus x squared over 2 dx. Okay? So now I can't use my argument of symmetry for sure, because here you have just a mapping that is, okay, an even 1. It's not odd. But you can just say that the integral between minus infinity and plus infinity here is just 2 times the integral between 0 and plus infinity, but it will give rise to the same thing. So how to compute this? fact that I'm able to know this one. You have an idea? So how much you obtain? So an idea first before to say how much. Nobody has an idea how to compute this?
By part.
Yeah. An integration by part, because I have this saved. Keep in mind what I have said here. Here I have used a trick in order to compute directly this expectation as 0 as the integral of a node mapping. But I have said to you that don't forget that this term has a non-primitive from the fact that I know what is the derivative of exponential of ux. In fact, it's exactly what we are going to do here. Okay, we are going to separate in two parts because in some sense I want to make disappear the x squared in order to come back to my previous case. Okay, and I will do it this way. X, I write x squared as x times x in fact. I do this one. And I will do my integration by part this way. I have here f of x. I have here j prime of x f prime of x will be 1 over the square root of 2 pi, for example, and j of x is equal to what? I have a known formula for this one because it is about up to a constant of the form u prime exponential u of x. So j of x is equal to minus exponential minus x squared over 2. So I can do my integration by part without problems here. I can do my integration by part without problems. And I do. So it's f times j between minus infinity and plus infinity. So I obtain here f that is x over the square root of 2 pi multiplied by j, that is this one, minus infinity plus infinity. And I have minus the integral between minus infinity plus infinity, f prime exponential minus x squared over 2 dx, and I have a minus that I have forgotten here, so I have minus, let's say here, and finish. So I do my integration by parts here. I do my integration by part. What I obtain here. So the limit in plus infinity and the limit in minus infinity of this term is what here? It's 0 because I have a negative exponential with a square here. So the limit of this one in plus and minus infinity is 0, and I multiply by a polynomial, so the exponential is always the best. Okay? And it remains this one, that is integral minus infinity plus infinity 1 over the square root of 2 pi exponential minus x squared over 2 dx. What is this integral? What is this integral? Well, it's the density of n01. So when I integrate the density, I obtain 1. And I obtain so that the expectation of the square is equal to 1 in the case of a Gaussian. We have seen together that the expectation of x is 0, so the variance is 1. And I see that in the case of a Gaussian of parameters 0 and 1, the mean is 0 and the variance is 1. Okay? So I have done the job for my n01. Now we are going to do exactly the same for nm sigma squared by using this. Here integration by parts. That will make disappear exactly what I don't want, that is this part, because I know that the integral of this part is 1. I have this one that I add in order to compute expectation or variance here. One idea is to use integration by part when possible. Okay. Okay. And now it remains to do what happened for nm sigma square. It will be that easy to do this because I can come back to the case of n01 this way. So if I have x, that follows the nm sigma square. Okay? I have this one. What I know, I have several possibilities to do this, but I can use proposition 13, okay, statement C here, to come back. So I have this one, and I want to come back to my initial case, that is to be n01. So I know from proposition 13 that x minus m over sigma follows the n01. And so I can use, okay, I can use what I have done previously for this random variable that follows the n01. So from my previous computation, I know that the expectation of x minus m over sigma is equal to 0, because x minus m over sigma follows the n01, and that the variance of x minus m over sigma It's equal to 1. Ask me the question, please. Or ask me.
This have the exponential, it should be the x, let us say 4 times x. It should be this by product.
No. Wait, what?
Because we changed the value.
No. I compute, look at me. I compute. Be careful of this. Huh? So I will write because it's a good mistake, let's say. But I will do the remark for everybody, okay? So you have the first formula in blue here. When you compute the expectation of x squared, okay, it's the integral of x squared times the density function. Okay? It's not. It's not this one, huh? Okay? It's not this one. Be careful. Okay? This one is not okay. This one works. So if I come back to my thing here, so I know that the expectation of this one is 0 from my previous computation. The variance of this one is 1 from my previous computation, because I know that if I start from n m sigma square x minus m over sigma follows the n01. Okay, but now I just have to use the property of the expectation and the variance in order to obtain what I want. Okay, that is this one. So what can I say about the expectation of x, and what can I say about the variance of x? Yeah. From this. Expectation is linear. So I can multiply this one by sigma and add m, and I obtain that the expectation of x is equal to. Okay. Be careful for the variance, it's not the same thing. Okay. For the variance, I have this I have these rules of computations here. If you want, you can use this one. Okay, but we have one of them. Okay, so you have two random variables here, but one is constant. What is the variance of the constant? Okay, so it means that when I do the job here, if you replace, okay, small a by 1 over sigma to obtain the first term, and, okay, b by minus 1 over sigma, and y by m, okay, but this term is 0, this term is 0, in fact I have a single term here. And what is this one from this one? Sigma square, clear for everybody? I have sigma square here. If this variance is 1, the variance of x is necessarily sigma square. When I do the job here, when you add or you subtract a constant in a variance, okay, it changes nothing. So you can remove this term here, okay, because, repeat, the variance of a constant is 0. Okay, so it remains the variance of x over sigma, the variance of x over sigma that is equal to variance of x over sigma square, according to these rules of computations here, and then I obtain that my variance is equal to sigma square. Okay, so here it's just the linearity that I use in order to obtain this, and here I use the rules of computation of variance, having in mind that the variance of a constant is reduced to 0. The only case where variance is 0. Okay? For a random variable to have variance equal to 0, it has to be a constant. You agree? So I have done the job for n01, and I am able to do in any cases. Okay? So maybe I will do the break now because I need a coffee. And after, the idea is to finish the course with this one, okay? So, I am in the following situation. So what is my aim and what is the interest of this proposition? You are going to start with random variables that are jointly continuous. Okay, so I start from 2. So I have a pair x1, x2 of random variables that are jointly continuous. Okay. So they have a joint density in the sense of what we have seen during the previous session. That is a mapping depending on 2 variables. Okay? F, x1, x2, the joint density. Okay. My question is the following. I want to transform the pair into a new pair. Okay? I transform it. So keep in mind that for a single random variable, it's a job I have done several times previously. Keep in mind that for n01, I have computed the distribution of x squared, for example. In the course, it's the place where I have defined the chi-square distribution. During the previous session, okay, I start with an uniform on the interval 0,1, and we have transformed it into the exponential of u, and see that it was possible to find its density function, but it was in the case of a single one. And in the case of a single one, I have said to you, I have a proposition in the course, that is this one, and I have said to you, not necessary to learn, in fact, because I can do it by myself, in fact, just writing the distribution function, computing the derivative of the distribution function in order to obtain the density function of the transform. Okay? So in the case of pair, in fact, the result that I will come back on just after is, in fact, a generalization of this proposition I have asked you not to learn a priori, because I prefer you to be able to do directly the job instead of learning the things that is stupidly. And the principle is the same here. So, x1 and x2, okay, I want to transform them into new random variables. Okay, so I defined 2 new random variables that are defined from x1 and x2. It's what I call y1 and y2, and I want them to be, okay, obtained from x1 and x2. So y1 is just g1 of x1, x2, and y2 is equal to g2 x1, x2. So it means that g1 and g2 are simply, for the moment, mappings from R squared into R, and the same for g2. And in fact, they are conditioned on g1 and g2 in order to ensure that the new pair you are going to obtain, okay, my aim is to see if this new pair is a pair of jointly continuous random variables, and if it's possible to obtain the joint density of the new pair from the joint density of the initial one. This is the aim of this proposition. And the answer given by this proposition is yes, but I need some hypothesis on G1 and G2. Okay? So I will be able, so I want to answer the 2 following questions. Are they jointly continuous, the new one? And if yes, what is the joint density of the new pair? Is it possible to express it from the joint density of the initial one. Okay, so technically something that is not very far from the little exercise I have done on transform of single random variables. Okay, but it's in the case of more than one. Okay? Is it clear what I have written? So I start from a pair of jointly continuous random variables with a joint density f x1, x2. I transform them, okay, meaning that I obtain new. You have a problem with the green color? No, it's okay? It's not that good, but I will use the white one now, okay? But so I define a new pair, and my question is, do we have some condition on the transformation in order to make this new pair jointly continuous and to have the joint density function? It's clear for everybody, this? And the answer is yes. The answer is yes. And to do this, okay, I need to check some condition on G1 and G2, and this is the aim of this proposition. So I won't enter into too much details, but if you have already heard about this one, in fact, the result that is below the proof of this proposition, okay, is maybe something that you will see in optimization soon. This is the change of variable theorem, okay, in integrals, but the change of variable theorem when you don't have a single variable but several ones, okay? So it's the change of variable theorem in dimension higher than 1, okay? Well, it's not something that I will use deeply in this course, but it is below the proof of this one, and in fact it's just a basic application of the change of variable theorem, okay? And I want just to discuss the hypothesis. So, how to check that G1 and G2 will be good candidates for what I want to do here, that is to find the joint density of the new pair. But in fact, if I do this, I can define, let's say, okay, a new mapping that is from R square into R square that associates to xy, G1 of xy, G2 of xy. Okay, I can call it, let's say, phi. Okay, so if I want to use this proposition, I need some condition on phi. First, I want phi to be bijective. Phi to be bijective from R square into R square. What is the meaning of this one? It's what is written in the statement this way here. So I have y1 and y2 that are defined this way, and I suppose that the transform may be inverted to obtain this one. To say that phi is bijective, it means that it has an inverse. So if I express y1 and y2 in terms of x1 and x2, to say that this one is bijective means that I will be able to express x1 as a particular function of y1 and y2, and to express x2 as a particular function of y1 and y2. This is the meaning that I can invert the transform. It means that this transformation is bijective from R square into R square. Okay? So I want something that is bijective first. Then I assume some regularity for phi. So if I use the language of optimization, so if you don't do optimization, forget what I will say just after, but it's just to make the link between both. The hypothesis that I will add after will tell me that phi, defined this way, will be a C1 diffeomorphism. C1 diffeomorphism. So what is the meaning of this one? What is the meaning of this one? It just means that phi is bijective, phi is C1, and its inverse is also C1. Not that complicated. Okay? And in fact, when we do analysis, it's what we call a change of variable. A change of variable is a mapping that is bijective, regular in the sense of C1, and its inverse has also to be C1. It's what we call the change of variable, okay, in mathematics. So it's what you do in general in dimension 1 when you apply the change of variable formula. You say, okay, I define z equal to x squared or z equal to the square root of, and so on, okay? So I want it to be bijective. I want it to be C1, and I want phi minus 1 to be C1. But in general, to prove this one may be a little bit tricky. Typically, for the second one, because it's not necessary that you have a nice formula for phi minus 1. Okay? But I have conditions that allow to check very basically if this is fulfilled, in fact. And it's what I write here. If I suppose that, okay, I have two mappings, G1 and G2, okay? I suppose that they have continuous partial derivatives, something that it will be very easy to compute. I will have to compute derivative with respect to x or derivative with respect to y. So if they have continuous partial derivative, and if this quantity here is not 0 with proba 1, it's different from 0 here. Be careful. I have seen a misprint in my slide. Everybody, listen to me here. Ah no, excuse me. So it's the probability that I am different from 0 is equal to 1, or the probability to be 0 that is equal to 0. So it's okay. Okay. I am not 0 with proba 1. That is, I am 0 with proba 0. Okay? And what is this quantity? So I have G1 and G2. I consider the matrix of the partial derivatives. That is G1 over dx1 dg2, dg1 over dx2 dg2 over dx1 dg2 over dx2. Okay, oh, excuse me, it's not x1 and x2, x and y that I have written. Okay, so I'll write it this way. Y, x, excuse me. So I just want to make the two notations the same, in fact, okay? So instead of write here x and y, I will use x1 and x2. It changes nothing, but just I want to use the same notation for the slides and the board, okay? So I have g1 of x1, x2, x1, x2, I have this, and here, thank you, I have this one. And what is the quantity in black? That is in the slide here. So here I have the matrix of the partial derivative. And what I compute here, what is this quantity? The determinant of this matrix. This one times this one minus this one times this one. Okay? So I won't use a lot of linear algebra in this course. Okay, you will see after the holidays a little when I will speak about random vectors. Okay, I will have a vector of expectation, the variance covariance matrix, and so on, but very few. Okay, linear algebra. Here I just need to be able to compute the determinant of the matrix of the partial derivative, and the determinant of the matrix of the partial derivative is in analysis something that you call as the Jacobian determinant of the transform. Okay, it's something that you use a lot in analysis and typically in optimization. Okay, so I want to do what? So concretely, what you have to do, you have to prove that you have something that is bijective, meaning that you can invert the transform. Okay, you have to prove this one, but this one may be proving that they have continuous partial derivatives. So you have to compute partial derivative and prove that they are continuous, and then to prove that this quantity, okay, has a probability 0 to be equal to 0. I want to be able to invert this quantity. If you are in this situation, meaning that if I am able to check all these statements, I have a conclusion that tells me that the new pair will be jointly continuous, and I will be able to express the joint density of the new pair. The new density the new joint density expressed this way will be obtained through this formula where you have inside here the initial joint density of the pair x1, x2, where you plug inside h1 and h2 that are the inverse transforms here. And here you have what? You have the absolute value of the inverse of this real number here at the point h1 and h2. Okay? So of course we are going to do several examples concerning the application of such a formula. Okay? But just keep in mind, in fact, so it seems to be complicated. I don't have the time to enter into the details of what I have below this formula, but it's just a change of variable in a dimension that is not, I don't have a single random variable, I have two. You will have the same statement for 3, 4, 5, and so on, okay? So below you have just a change of variable formula, and in fact, what you have to check is that I have these two things, and to prove these two things, I have to be able to invert. I am interested in the matrix, the partial derivative of each transform G1 and G2. If I prove that the partial derivative exists and are continuous, I know from analysis that I have something that is C1. If I have this determinant that is not zero, that is the determinant of the matrix of the partial derivative that is not zero, but directly I have this one. Okay, so it's what you have here. So let's use maybe, instead of saying more, we are going to have a look on an example and see how to use these results. Okay? That is, okay, my aim will be how to obtain new joint density function. Okay? So let's do the job with one example. In fact, I will come back to something that I have already do with you. So I erase everything because I have my slides, okay? So, what will be an exercise around this question? I will give you a joint density to begin with. I will give you a transform, and I will ask you to find what is the new joint density, okay? So it's the way you will use this if I ask you to do. And typically, concerning this proposition, I will give you an homework to do for the holidays. Okay? I will send it to you by email. It won't be a big one, okay, but something around this. In order to define distributions that will be used in the statistical part. Okay? So, example of use of this proposition. So I am in this situation. I start with x1 that follows an exponential of parameter lambda. Why not? I have x2 that follows also an exponential of parameter lambda. Why not? I suppose them to be independent. Why not? And I ask you, okay, the following. Find if it exists the joint density of what? Of this pair here. x1 plus x2. Why not? Okay. So I start from x1, x2, and I want to obtain the joint density of the pair x1 plus x2. Okay? Here? Okay. Typically, the aim of my proposition. So when you do this, okay, in particular at the beginning, okay, be careful concerning the way to use this one and try to be, okay, rigorous in the way to use it. So, I have my transform here because I give you everything. So what is G1 and what is G2 here? So G1 is a mapping from R square into R that associates to x1, x2, what? you have here, with my notations, here you have here what will be y1 and what will be y2. So what is g1? x1, yeah. Just the first coordinate, because if I transform my vector, the first coordinate remains the same. So I am identity in the first, and for the second one, is what? Yeah, you don't have the choice. You have everything that is imposed by the transform x1 plus x2. So it's nice here because I don't have to work too much in order to do the job, because I transform linearly the initial random variable. So to find that I am bijective, to find that my partial derivative exists and are continuous, I will have to deal with a polynomial of degree 1 and several variables. So it will be very easy. So for the moment, I have said nothing. Okay, I am at this stage of the statement. I am here. I have defined my transform here. Okay? So now I have to prove that I can invert my transform. That is, I can express the new and the old random variable in terms of the new. Okay? This is the meaning of invert. So I have what? I have y1 that is equal to x1. y2 that is equal to x1 plus x2. It's not that complicated to find what I want. In this particular case, you will have some cases where it will be a little bit more complicated, but here I want to express x1 in terms of y1 and y2, and x2 in terms of y1 and y2. So what I obtain for x1, if I want to express it in terms of y1 and y2, I don't have the choice, it's y1. And for the other one, I have x2 that is equal to y1, excuse me, y2 minus x1, but x1 is y1. So I have this, okay? I have this one. I have inverted my transform, meaning that the h1 and the h2 involved in the slides are h1 from R2 into R that associate to y1, y2, y1, and h2 from R squared into R that associate to y1, y2. What? That associates by the difference between y2 and y1. So I have proved that the transform may be inverted to obtain exactly h1 and h2 and h2 that will be needed here at the end. Okay? And I have them, exactly. Now I have to deal with the fact that g1 and g2 have continuous and partial derivatives. In this situation, I have nothing to say. You have polynomials here. Of course, they will have partial derivatives that will exist and that will be continuous. Okay? So I have nothing to say because I have classical mappings here that I know to be okay with a great regularity. So for G1 and G2, partial derivatives exist and are continuous without problem, and I will write the matrix of the partial derivatives here. So if I write the matrix of the partial derivative in order to be able to compute the determinant here, so here in the first position I have the derivative of G1 with respect to x1. What is this? Derivative of J1 with respect to x1. Derivative here, derivative of J1 with respect to x2. Derivative of G2 with respect to x1. Hmm? And with respect to x2? Okay, if I compute the determinant of this one, I obtain what? A 1. 1 that is never equal to 0. So I have checked everything in the statement, and I can conclude that the new pair is a pair of jointly continuous random variables, and that I can obtain the new joint density for the last formula in red in the slide. That is the joint density of y1, y2 at the point y1, y2 may be expressed this way. So a nice feature in this situation is that if you compute here the absolute value of the inverse of the determinant, you obtain a 1. Okay, so I have two terms to compute here, this one, and this one in my situation here is simply equal to 1. Okay, so I will have something time 1. Okay, and then I have to find what is the joint density of x1, x2 at the point h1, y1, y2, h2, y1, y2. And the one here comes from this part that has shown to be equal to 1 from this little computation. But now it's almost finished. Keep in mind that what I have done here, I have just used my proposition. I have never used this. Never used this. Okay? I just handle the transform and say that I can use this definition here. It means that if I change my initial hypothesis, I can do exactly the same. It will be what I will do for the second example. Okay? It just depends for the moment what I have done, just depend on the transform I have considered to change x1 and x2 into x1, x1 plus x2. Okay? So if I want to obtain this term, I need to use my hypothesis. What I know, I need to know the joint density of x1, x2. But what are my hypotheses? I have two random variables that are independent, and I know the density of each component. From what we have seen yesterday, it was here. If they are independent, the joint density is just the product of the density of each component. Okay? So I will do it in 2 steps. So I have f of x1 at the point h1, y1, y2 multiplied by f of x2, h2, y1, y2. Here I have just used the independence from the statement. Then, if I don't use independence, if I use now the fact that I know the density of each component, I can plug because I know what is the density of an exponential of parameter lambda. I know what is the density of an exponential of parameter lambda. I know what is h1 of y1, y2. It is just y1 here. h2 of y1, y2 is just y2 minus y1. And if I plug inside, I obtain lambda exponential minus lambda what h1, that is y1. Indicator function y1 positive. And then multiply by this term, that is lambda exponential minus lambda y2 minus y1, indicator function of y2 minus y1 positive. So I repeat what I have done here. I have just used the fact that I know the density of x1 and the density of x2. They are exponential of parameter lambda. I know that h1 is y1, that's why I have y1 here and y1 in. h2 is y2 minus y1, that's why I have y2 minus y1 here and y2 minus y1 here. And I have done the job. I can simplify a little. You see that you have a simplification between this term and the term that is here. And I obtain what? I obtain lambda square exponential minus lambda y2. So what is this? So I have indicator function that y1 is positive, and here the indicator function that y2 is greater than y1. So I can write it this way, indicator function of y2 greater than y1 greater than 0. And do you recognize this? If you were present during the previous session, it's a computation I have done here. It was the example of a joint density that I have shown you. Okay, it was this one. That is exactly what I have written here. Okay. Just a remark, and after I will comment what I have done. So at this stage, I have the joint density of the new pair. Okay? And I repeat that it is someone I have already studied in a course. Okay? Something that was defined in slide 11, this part. For this density, I have also done some computation during the previous session. Because I know that once I have a joint density, this one, I can recover the density function of each component computing partial integrals. If I compute the integral with respect to the second variable, I obtain the density of the first component. If I compute the integral with respect to the first variable, I obtain the density of the second component. And it's a job I have done in this situation. So in this situation, when I have started with this joint density, I have found, or we have found together, the density of x and the density of y. It means that since I recover exactly this joint density, in the course you have the computation that gives you how to obtain the density of the new pair, of the components of the new pair, that is the density of x1. Of course it's an exponential of parameter lambda, but we have seen what is the density of this one, and I have done the computation explicitly here. Okay, during the previous session. So I will finish by this for this example. Okay, so what is my methodology when I use? So first the type of the statement. I have hypothesis here that will allow me to obtain a joint density at the beginning. It will be the joint density of the initial pair I deal with. Okay? Then I use a transform. If I want to find the joint density of the new pair, I have to check that I am in the statement of this theorem. So first, here I have to identify my transform to check that I can invert this transform, then to prove that this transform have continuous partial derivatives, to compute the matrix of the partial derivative, to see that the determinant fulfills this condition. Here I am not 0 with proba 1. Here it's nice because I am not 0 everywhere. Okay? So with proba 1. And then I can apply the formula that gives me the density of the new pair in terms of the density of the initial one. Okay? So let's see another example. So do you have some questions? Yeah?
When we use J of x1 is 2 is directly the determinant of the Jacobian matrix?
Yeah.
Okay.
Yeah. Okay. It's just the determinant of the matrix of the partial derivative. Something that you will use and you have already used a lot in optimization.
Yeah, but I didn't know if only J was directly the determinant of the matrix.
No, I have erased, but if you write the matrix of the partial derivative, okay, what is the matrix of the partial derivative? You have in the first position, first line, dj1 over dx1, dj1 over dx2, dg2 over dx1, dg2 over dx2. If you do the determinant, you obtain exactly this. Exactly. And I want this determinant not to be equal to 0. And typically, because I want to be able to plug inside here, if it is 0, since I have to take the inverse, it's a number, this one, huh? Okay? So when I write g minus 1 here, it's just 1 over this quantity here. Okay, it's the inverse of a number. J is not a matrix here; it's a number. Okay. And since I want to divide by it, I have to check that it is not 0 with proba 1, okay? It's my hypothesis, and I obtain this new density. So a second example here, when we are going to see that I can change a little bit the statement in order to obtain a lot of possible exercise. So second example, that I will keep on the board almost everything except this. I change this one, and instead of starting with exponential of parameter 1, parameter lambda, I will start with 2 and 0, 1. 2 independent and 0, 1. Why not? And the question is exactly the same. I want you to find the joint distribution of the new curve defined as x1 and x1 plus x2. And typically from this one we are going to be able to deduce after some computation what is the density of x1 plus x2 when x1 and x2 are 2 independent and 0, 1. We are going to prove that it is the density of n02. But let's see. So suppose that you have the statement here. Okay? I want you to do this. In fact, I can keep almost everything here. What I have to erase? I have to erase nothing. So this one, I define the transform. I check that I can invert them. I check that the determinant fulfills the good condition. I apply my formula. The determinant is 1. Here, I have this one because of independence. The only thing that I have to change is this expression here. Okay? It's this expression because everything works. At this stage here, I have used only the independence. I don't use what is the density of x1, I don't use what is the density of x2. Okay? So, I have to do the job now with the new density. x1 follows the n01. I know the density of n01, 1 over the square root of 2 pi and so on. Okay, so it's 1 over the square root of 2 pi, okay, exponential minus y1 square over 2. Here I don't have indicator function because the density of a Gaussian is strictly positive everywhere. Okay, so I don't have indicator function in the definition, and I have here 1 over the square root of 2 pi exponential minus y2 minus y1 square over 2. I have this. Why not? So you have here the joint density. So if you want, you can develop a little, okay? You can develop the square and see if I have some simplification. But in fact, I won't have that much simplification. It's a computation that I will do just after, but I will obtain y2 square minus 2 times y1 y2 and plus y1 square. So I will have maybe some little simplification between the y1 square, okay? But at this stage, my joint density is given by this one here, okay? In 2 hours, you will see that here you have the density of x1 and here you have a conditional, what we will call the conditional density function. But let's see this after the holidays. Okay, so I have my joint density. Okay, so now I continue my exercise in some sense. So you have the joint density, okay, using the proposition 16. And my question is, find the density of y1 and y2. Find the density of y1 and y2. Question? Sure? So y1 is not that complicated. What is the density of y1? Y1 is x1. x1 is the n01, so y1, okay, follows the n01. So I have its density. No choice. The only part that is interesting in the question is find the density of the sum here. So I come back to the proposition 15. If I have a pair having a joint density, if I want to obtain the density of the second component, I just have to integrate the joint density function with respect to the first variable. Okay? I have to integrate the joint density function with respect to the first variable to obtain the density of the second component of my vector. So here, if I want the density function of y2, I just have to integrate this mapping with respect to y1 and see what happens. Okay? Or not? It's exactly what you have here. If I have a joint density function, so x and y, okay, are jointly continuous, I said that in order to obtain the density of x, I just have to integrate the joint density with respect to y. In order to obtain the density of the second component, I just have to integrate the joint density with respect to the first variable. Okay. So now I can erase all these things here, okay, and I will just focus on my joint density. And I know from the course that in order to obtain the density of y2, the one that interests me, the density of y2 is obtained through the proposition 15 by the integral between minus infinity and plus infinity of what? Of the joint density of y1, y2, and I have to integrate with respect to y1. Okay? I have to do the job. I have to compute an integral. Okay? So let's compute this integral. So it's, a priori it's not that simple, but we are going to see that in fact I know how to. I know because it is from the course. So I have, let's say that I have 1 over 2 pi because I multiply the square root, okay? I have 1 over 2 pi. So if I develop the square here, I obtain what? I obtain exponential minus y2 square over 2. Then I have minus the double product, but with a minus here, okay? So I have plus y1, y2, okay, plus y1, y2 here, okay, and then I have what? I have minus y1 square over 2, minus y1 square over 2, I have minus y1 square over 2 also here, so I will obtain minus y1 square, okay? And I have to compute this integral with respect to y1. Okay. My question is how to do. And my answer is to use what I know. So I have this integral to compute with respect to y1. Okay? So when I see this, what I see? I see that I have exponential with squares inside the exponential. Okay, I have exponentials with, in the expression of the exponential, I have square. Okay? If I have a look on the distribution we have seen together, okay, here I don't have such a thing, here I don't have such a thing because I have an exponential but without squares, okay, and I have this one. I have this one, that is a density function, okay? And I know that if I develop the square here, I will obtain x squared and so on, okay? So it means that this one seems to be not very, very far from this kind of expression here. The only difference I have between this one and this one is that here you have a perfect square. And here I don't have. It's not a problem. We are going to make appear a perfect square, okay? And use what we know about the Gaussian density function. So let's do the job this way. So the idea, okay, is to handle a little this expression here in order to express this way with a square. Okay? The square in what? And keep in mind that my square is in x, my variable here. So I want a square in y1. That's what I need to have in mind. Okay? Okay, so what can I do? So before to do the integral, I can say the following. Minus y1 square plus y1, y2 minus y2 square over 2. I will try to make appear a perfect square in y1. Okay? So first I have a minus here. So if I want a perfect square, it will be something like this. So if I want to obtain y1 square, I put in my square y1 here, and I obtain the first term. This one is okay. If I want to obtain this one, okay, what I have to do? Minus y2 over 2. And if I do the job this way, when I will do the double product with the minus, I will obtain minus y1, y2 with the minus before, so I will have plus y1, y2. Okay? And how to finish? But in fact, I have done the job here in order to make appear this one and this one. Okay? But if I introduce this term here, but it is not present in my two first terms here. So if I introduce it, I have to subtract it. What I obtain, if I do this, I obtain plus y2 square over 4 with a minus. So minus y2 square over 4 if I do this, okay, I repeat, if I do this, why I have done these jobs? Because I don't have color anymore, too much. Here, this expression here, the two first term is exactly equal this one, exactly. I do the job in order to make appear what I want, and then I have something that is more, so I subtract because I don't want it. Okay? And I repeat, the idea is to make appear a perfect square in y1 in order to be not very far from this kind of expression here. But if I do this, I don't have to forget that there is a missing term here, that is this one. This one that I have to add here, minus y2 square over 2. And if I continue my computation here, we have seen that minus y1 square plus y1, y2 minus y2 square over 2 can be written as minus y1 minus y2 over 2 square, and I can simplify this one, and I obtain minus y2 square over 4. Okay? I have this one. I repeat, why I do this, it's not for the pleasure to compute, it's because I want to compute integrals with exponential of square inside. I want to come back to what I know. And I know that the integral of all these quantities are equal to 1. Okay, it's what I want to use. In order to use this, I make appear this part here, that is the analogous of what you have here. The perfect square that is here, with a minus before. Minus a perfect square. Okay? I can continue to do my computation. I keep in mind that I want to compute my integral. What I want to do. So I have this parenthesis in green here, that is just handle what I have in the exponential. I have handled it this way. And so I continue my computation here. The integral I want to compute is equal to what? It's equal to the integral minus infinity plus infinity, 1 over 2 pi, okay? Exponential minus y1 minus y2 over 2 square minus y2 square over 4 d of y1 is this one that I have to compute. So first I have to compute an integral with respect to y1. I can remove from these integrals all the terms that doesn't depend on y1. So I can remove exponential minus y2 square over 4 and 2 pi. And then it remains to compute this one. Now I said that to compute this integral is a question from the course, it's not a question from computing. Because I have done everything in order to be able to recover something that is in the course. So have you understood this computation here? So you see that I have an integral that seems to be a little bit complicated to compute. With inside you have squares, okay? The idea, it's the first time we see this, but you are going to see that we are going to do this a lot of times, okay? Is to come back to the Gaussian case in some sense. That is to make appear perfect square. Perfect square in what? In the variable with respect you want to integrate, okay? So it's exactly what I do here. I express this quantity using a perfect square in y1 here. I compute my integral this way, and I come back to be able to compute this kind of integrals. And I said that now, to compute this integral is just a particular case of knowing the fact that this integral is 1. So are you okay with this one and this one? Everybody? So I will erase this part because I want to keep this on the board for the moment. I will erase this, and I have to compute this. And I will show you that it is a consequence of my definition of the density of an m sigma. If I take my slide and if I take the formula in blue, I know that its integral is 1. So it means that I also know that this kind of integral is equal to this. Okay? Just using the fact that this integral is 1, so the integral of, the integral of the exponential is equal to the square root of 2 pi sigma square. Okay? I have written nothing here. I just say that here I know that I have a density function, so its integral is 1, and so that the integral of the negative exponential is just equal to the square root of 2 pi sigma square here. Okay, so I say nothing. How to pass from what I know to what I want. So here I integrate with respect to y1, so my variable of integration is this one here. The same as here. I see that if I take particular coefficients, I will be able to recover exactly what I want. If I take m, that is equal to y2 over 2, and sigma square to be equal to 1/2. I have exactly what I want. If I take m equal to y2 over 2 and sigma square equal to 1/2, when I plug inside this expression here, I obtain exactly the integral I am interested in. Exactly this one. So if I do the job, I have this. I have this one. Simply, I plug these two constants inside this relation and I obtain that this one, that is exactly the integral that interests me, is equal to the square root of pi. So this one is equal to the square root of pi from what I know from the Gaussian distribution defined in the course together. And now it's finished because I plug inside, this integral is this one, I have this expression, I have the fact that the density of y2 is equal to what? I simplify a little what I can simplify, that is 1 over 2 square root of pi, okay, exponential minus y2 squared over 4. And what is this density function here? I said that it is a density function from the course. Is it possible to compare what I have here from what I have here? But yes, it's possible. I take m equal to 0. If I take m equal to 0 and sigma square equal to 2, I have what I want. y2 follows the m0, because it has this density function that is none other than the density function of n02, knowing my definition. So I have done the job, I have proved what is the density function of y2, and the result we have below this computation is that if I start from 2 independent in 0, 1, if I do the sum follows the n02. Okay? And we will see together next week that it's a general thing concerning Gaussian random variable. Okay? If you do the sum of independent Gaussian random variable, you obtain a new Gaussian random variable with a mean that is equal to the sum of the means and a variance that is equal to the sum of the variances. Here it's just one particular example using proposition 60. Just a last question before to finish this example. So what I have the joint density here of the pair y1, y2. I have the density of y2 obtained computing the integral of this one with respect to y1. That's exactly what I have done here. I know that y1 is equal to x1, so I know that the density of y1 is the one of n01. The last question is, are y1 and y2 independent? Are y1 and y2 independent? You have the joint density of y1, y2. You have the density of y1, you have the density of y2. You have a criteria in order to check if they are independent. They are independent if the joint density is equal to the product of the density of each component. So I repeat my question, are they independent? No. Because if you develop the square here, you will have a term that is the double product, y1, y2. And in fact, it won't be possible for you to express the density this way, because you will have this term, an exponential of y1, y2, that you won't be able to separate in the product of two terms, one term depending only on y1 and one term depending only on y2. So directly when I have a look on this density function here, this joint density function, I am sure that the underlying components are not independent, because I have a term inside here where I can separate the variable y1 and y2 inside. Okay? So they are not independent. Okay? So it's typically, okay, a typical example or exercise dealing with this proposition. Okay? We are going to see in the list of exercise other exercise of this type. Okay? So it closes the course concerning continuous random variable. Okay? Next week I will do moment generating function. That is a short part, just something that is powerful to handle, okay, typically for continuous random variable. And we are going to finish with the beginning of an exercise here today. That is a long one, so I will finish it next session. You take the list 5, and it's the exercise 5. This one. In this exercise, we are going to define a random variable or a distribution that I will consider as a distribution that you have to know in the course. That is the gamma distribution. Okay, so the aim of the exercise 5 is to introduce what we call the gamma distribution. We will see that the gamma distribution, okay, is an extension of some distribution we already know. Typically an extension of the chi-square, an extension of the exponential, okay? That is that easy to handle. But before to be able to define this gamma distribution, okay, I have to do some things about integrals, and I want to finish by this today. In particular, doing the first question of the exercise 5 here. So, okay, so exercise 5 of list 5. And I think that it is a very good idea to try to finish it by yourself at home during the weekend for next week. So it's a little bit long, okay, but really good exercise to see if you have understood, okay, the things we have seen together. And I will finish the correction next week, okay? Okay, so I define a mapping, okay, that is called the gamma function. So maybe you have heard about this function or not, whatever. If it's the first time, just I define it this way. I define gamma of alpha as the integral between 0 and plus infinity of what? Of exponential minus y to the power alpha minus 1 dy. So, in analysis, okay, this mapping is really famous for a lot of property it has, okay, really a lot of, but one that is very nice is that it is something that is very regular, okay, so the dependence in alpha is in fact very regular, okay, meaning that I am continuous, in fact differentiable and so on and so on. And that, okay, you have a regular mapping that coincides with the factorial for integers. Okay? So you have a mapping, when you plug inside n, belonging to capital N, you obtain n minus 1 factorial. So you have a mapping that, if you want, extrapolate all the factorials, and that is very regular. It's one of its quality. Okay? Here, whatever, it will be used in order to define a distribution. Okay, so I have this integral here. Okay? A priori, I repeat that in my course and typically for the final exams, okay, I won't spend my life, okay, in asking you, is this integral well defined or not? In general, all of them will be well defined. Okay, the one I will propose to you will be okay, and you will have to do computation. But a priori, when I have to compute an integral, I have a step to do before to compute, that is to show if it has a sense to write this integral. That is, here, defining the integral this way, I obtain a number or not. Okay? And I may have some conditions of what I have inside the integral in order to ensure that I have the convergence of the integral. Okay? Yeah? And come back to the notes I have in my web page, okay, concerning integration. It's something that I explain. So here, but when I see this integral, okay, I say that I have two problems, in fact. I have two problems. Why? My first problem is that, to be sure that I define something that is perfect, okay, my first problem is this. I have plus infinity, so it means that it's something on an unbounded interval. I have to check, okay? And what I will have to check is to consider, in fact, I have a limit to compute or a limit to prove that it exists, okay? Okay, so in this expression, I have first to show that a limit exists. Okay. Second problem I have, in fact. If I write the things this way, it's not that easy to see, but if I write this integral this way, I see that I have another problem. I have another problem because y may be 0. Okay? So it means that the mapping inside is not necessarily defined at the boundary of my interval here. So what happened for its integral, I don't know a priori. Okay? So I have a problem in plus infinity, and I have also a problem in 0. Okay? Yeah. And I have to solve both of them in order to see that I don't have, in fact, a problem with this integral, so I don't have a problem. Be careful, I won't have a problem if I impose a good condition on alpha. So, it will be the last time I will do this kind of reasoning, but I just want to show you that I have to take care, a priori, if I want to deal with integral. For the exams, okay, I will take care for you, okay? But a priori, when I have an integral, before to compute it, okay, directly, just 1 second to answer if it exists or not, okay? So here I have two problems in plus infinity and in 0. In fact, I don't have problem, or I am able to solve them. In 0, okay, I am interested in this mapping. This one, okay? And what is the term that bother me in this expression? But it's what I have in the denominator here, because the denominator can be 0. What I have in the numerator, I don't mind, because at 0 it's 1. Okay? So I can say the following. This one is equivalent in the terms of analysis when y goes to 0 to 1 over y 1 minus alpha. Okay? Just because exponential of 0 is 1. Okay? Just because exponential of 0 is 1. But if you have read the notes I have done on integrals, you know that if I want to compute this kind of integral that are called Riemann integral, okay, I have a criteria in order to have this one finite. And when I mean well defined in the things, it means that I have a finite number. In fact. What is the criteria here for this one? What is the criteria?
A is higher than 1.
Hmm?
A is higher than 1.
No, no, just I don't understand. I don't have. It won't be a criteria on X. Huh?
I said that alpha needs to be less than 1 otherwise
Yeah.
it would be convergent.
Okay. I'm agree with you. If I want this integral to be okay, A strictly less than 1. Okay? It's the Riemann criteria for this kind of integral. So, don't seem to be surprised, okay? Because if I come back to my little document, here, this one, okay? You have inside, in the example 5, exactly what I say here. Okay? That this kind of integral are well defined if the coefficient is strictly less than 1. So, in what I am interested in here, it's not x to the power a that I have, but y to the power 1 minus alpha. If I want the integral around 0 to be well defined, okay, that is, if I want to solve my problem at 0, I need to impose a condition on the coefficients, that is, 1 minus alpha has to be strictly less than 1. And what is this condition? Is in fact alpha strictly positive. Okay, so it means that if I impose alpha to be strictly positive, in fact I don't have a problem at 0 for this integral. The only problem I may have is the problem at plus infinity. Okay? So everything is explained inside. Maybe I have, typically, yes, I have done this. Okay, you have exactly this, what I said as an example of what I have in my notes. Okay? So, I am able to solve the problem at 0. Okay? If alpha is supposed to be strictly positive, I don't have a problem here. So the last question is if I have a problem at plus infinity or not. But why I don't have a problem at plus infinity, in fact? Because I have a particular function here. Okay? In plus infinity, when I see this, okay, and when I look at plus infinity, I don't mind about this one. This one that matters. I have a negative exponential. And in fact, I don't have a problem to integrate something that is, let's say, a negative exponential multiplied by a polynomial or multiplied by a numerator, something like this. Okay? So the problem in plus infinity, in fact, is not a problem anymore. So if you want to write it correctly, and come back to math notes, okay, to say that I don't have a problem in plus infinity with this kind of term, I can say the following. So it was at 0 here, and in plus infinity now. To solve my problem in plus infinity, I can say the following. So you know that what happened for this one when y goes to plus infinity? At 0. What happened to this one when y goes to plus infinity? 0, so I can put everything before, okay? But what is the meaning of this one? It means that this one goes to 0, okay, when y goes to plus infinity. So for large y, I am bounded, in fact, if I goes to 0. Okay, so I can write it this way. There exists an m belonging to R plus such that for all y greater than this m, that is for y large enough, because I am interested in the limit in plus infinity, I can say that I have this exponential minus y alpha minus 1 will be less than 1 over y squared, for example. Because if I go to 0, when y is large enough, I am typically less than 1. That's what I write here. And I said that this inequality solves my problem in plus infinity. Because now I want to integrate this mapping, okay? I don't know if I have a problem or not at plus infinity, but I know that it is less than this one. Okay? It is less than this one, but I know that this one is integrable at plus infinity. Because I have this criteria at 0. Okay? I have this criteria at 0, and I have the same criteria in plus infinity that tell me that these kind of integrals are finite, okay, from 1 to plus infinity, if and only if a is strictly greater than 1. And it's exactly what I have here. I have y 1 over y squared, that is 1 over some 1 to the power a, with a that is strictly greater than 1. So at 0, using an equivalent, I prove that to study this one or to study this one is the same. At 0, I have a nice criteria for this one. Okay, I just have to check if the condition on the power are fulfilled or not. This condition being 1 minus alpha strictly less than 1, implying that alpha has to be strictly positive if I want to solve my problem at 0 in the definition of this integral. In plus infinity, if I have a look on this one, okay, I see, okay, I have a negative exponential, so it goes very fastly towards 0 in plus infinity, so I won't have a problem to integrate. If I want to write it correctly, I can say, okay, I have my mapping I am interested in. If I multiply by this one, for example, it goes to 0, so it is less than 1 over y squared. This one is integrable with respect to this criteria, because the power 2 here fulfills this condition, and so my integral is well defined here. So, if I come back to what I am interested in, that is my exercise. A priori, if I want to be totally correct in the way to answer this question, it's what I have to say. Okay? What I want you to know from now on is that these kind of integrals are well defined for alpha strictly positive. Okay? And alpha strictly positive comes from this one, that is the condition at 0. That's why I need to impose this if I want here to obtain a number. Okay? So, all these arguments are details in the little document I have written concerning integrals. Okay? But I repeat that it's not the kind of question I will ask you for the exams, to be totally clear. Okay? But I just want you to keep in mind that if I do integration, I need to do things before to compute. Okay? But it will be the last time that we will do this. Okay? Now I just keep in mind that if I have this kind of integral, okay, I make them well defined, imposing that alpha is strictly positive. Okay? Okay. And I have to stop because I have to finish 10 minutes before. So see you next week. I will finish the exercise. Try to do, okay, at the very least, the first question. Here it's just a basic computation. Here you use integration by part to do the job, and then you have to compute expectations and so on. So try to do, okay, spend a few minutes on this during the weekend. I will correct it, okay, next session. Okay? See you.